What we've got here is the register file from my SPAM-1 CPU. It's made from a bunch of 4x4 register file chips. This is the 74670 that I've talked about in my previous video. They're arranged in pairs because this is a 4x4 chip, so 4 latches, each of them 4 bits wide. If I combine them in a pair, I get 4 latches, each of them 8 bits wide. And this register file is a triple port register file, so 1 port in, 2 ports out. So I've got 2 pairs of those register file chips, and this gives me 4x8 latches, another 4x8 bit latches. So 8 bits in and 2 lots of 8 bits out. And of course, because there are 4 latches in here, there's addressing to determine which of the 4 latches is going to get written during an instruction, and there's 2 output channels, so there's addressing to control which of the 4 registers appears on each of the output channels. And this diagram illustrates this architecture. 2 output channels from the register file, 1 channel in. So there's your 3 ports. The 2 output channels from the register file feed the ALU. There's 2 inputs to the ALU. There's actually other channels from inside the AM CPU that get multiplexed onto those 2 buses, but I won't speak about those right now. And we've got the address lines to control which of the 4 registers that are in here are going to appear on the outputs and are going to be updated by the next input. Now, if I wanted to build something similar to this circuit here using discrete logic chips, I'd end up with something like this. And you can see there's quite a few chips here. There's some latches. I've suggested you could use a 74373, 4 of those, 4 times 8 bits. And then we want to multiplex these latches out onto the 2 output channels. And I suggested you could do that using 74245 transceivers. So we'd have effectively a 32 to 8-bit multiplexer. And you'd have some decode logic to go with that to decide which of the latches is going to get written to and which of the output transceivers is going to have access to the bus. So you're looking at about 15 chips there versus, say, the 4 I've got here. But there's also this register, and I haven't really explained why that's there. And just let me get to that now, actually. It's due to the fact that these register file chips here are level-sensitive devices. They're latches, after all. They're not edge-triggered flip-flops. And in my particular configuration, where these are feeding the ALU and the ALU is looping back into these registers, there's a problem. Let me just show you that. So if you consider this diagram here, imagine the output of the ALU, sorry, the output of the register is, say, 0, and the ALU's operation is not A, so it's going to invert that 0, and we're going to end up with FF here on the output because it's 8 bits wide. Well, with this as it stands, and this being a latch, what would happen is that FF would loop around back into the register, and because this is a latch, it's transparent, that FF will appear on the output after 1 propagation delay. Well, this is going to invert it again, it's going to be 0. Right, I hope you can see what's going on there. We've actually got an unconstrained feedback loop there, and this thing is actually going to be an oscillator. In fact, it's going to be an 8-bit oscillator, and that kind of behavior is kind of basically useless for my needs. I need something that's more deterministic than that, for sure. So the approach I took, pretty simple really, was to throw a flip-flop at the input. So this flip-flop only loads a value from the ALU on the positive edge. So what I've done is I've taken the right enable line of the register file and inverted it. So on the falling edge of the right enable line, I get a positive edge on the flip-flop, which causes it to load the value just at the beginning of the write cycle. And from that point, it doesn't load anything else. It's no longer sensitive to the input. But now we've got the value fixed here on the data in of the register file. And while this remains low, that value propagates out onto the output. So yeah, sure, you're going to get some kind of feedback, but it stops here. And when that line goes high, the value that was present at the input is now latched inside this register file at the address that was selected by the right address line. So that completely cures my feedback problem. Whether that would work for you with this particular chip, it depends on the timings inside your CPU. Mileage may vary, but it works really well for me. But what we really need is a demo. So as I said, this is the register file here. This board at the top is actually just a collection of switches and lights that are taking the 2 outputs of the register file and displaying them here, and a bunch of switches that allow me to control the address lines and the data lines going into the register file, just for the purposes of demonstration. So let me just hook this thing up to some power and get this ribbon cable put back in place, and let's take a look at it. Right, so as I said, there's some control bits for what register is going to get written. So there's 2 bits there controlling write address, and then I've got 2 output buses. So 2 bits identifying which register is going to appear on bus A and which is going to appear on bus B. I've got some switches controlling the data input. I've got a switch here controlling this input register, which I haven't really fully explained yet, but I'll get to that. And another switch controlling the write enable for the register files themselves. So at the moment, all of the switches are set to 0, so the write address and the read address is register 0. So if I put some recognizable pattern on the data, let's just put the top and bottom bits to 1 and toggle that button, then the input latch has now registered that signal. Now, if I want to write it into these register files, I need to toggle their write. Okay. Now, if I then switch the write address to, say, register 3 by putting both of those bits high, and let's say I put all of the data bits high too, then latch that value into the input register, I can then latch it into the register file. Now, of course, these displays haven't changed because they're still set to display the value of register 0. But I'm confident that I've just written that value into register 3. So if we change, say, for instance, this channel B to display the value of register 3, there we are, we can see that indeed I did write it. And if I flick this one to also look at register 3, we can see it over there too. And of course, the old value is still back at address 0. Now, I've seen some discussions on the internet about how to use 74670 where some sort of synchronous behavior is needed. And one of these solutions that I've seen talked about is one that I'm not at all a supporter of, and that is generating some kind of very short pulse somehow. Well, how short should that pulse be and how long can it be? Well, if it's too short, let's say it's shorter than the propagation delay of the register file, well, this isn't going to register the update properly, and that's something like 23, 25 nanoseconds, something like that. But if that pulse has to be short enough that it prevents the feedback, or it doesn't give the feedback enough time to have an effect, it's got to be less than the propagation delay of the ALU. So let's say the ALU is something like 70 nanoseconds propagation delay, and this is 23 nanoseconds propagation delay. Well, then that pulse has to be longer than 23, but less than 70. That's just really way too fragile for me. I don't want to build circuits like that. And this is, for me, the way to go. It doesn't rely on any kind of tricky pulse width management or anything else like that. I'll provide a link to this circuit in the notes at the bottom. Something else that helped me design this was plotting a timing diagram. This example here was created using a tool called Wavedrom. Again, like everything else I've done in SPAM-1, I have a simulation of all of this created using Verilog. And again, I'll put links to that in the description at the bottom. If you're interested in Verilog, at some point I will probably do a quick video on what I wish I'd known and what I've learned. And I'll also probably cover a few of the chips because I had to recreate models for a bunch of the chips I've used because what was out there was either incorrect or didn't have the timings. So anyway, hope that was useful and interesting, and see you again.